This video on 1.1 vectors will look at exercises 5, 6, and 7, which discuss vector operations, in particular scalar multiplication and vector addition. When we combine these two operations, we can get a result of a vector called a linear combination of two other vectors. When we look at scalar multiplication, we take one vector and we simply resize it. So what we are doing is changing the horizontal and vertical components by the same scale factor. And we can easily see this if we make a right triangle out of the blue vector, that we are coming up with a base, or delta x, and a height, delta y. And then if we resize that blue vector, we're not changing the direction of the vector because the red and the blue vectors are parallel, but we are changing the length or the magnitude of that vector. In other words, we are scaling the triangle to a new triangle with all same angles. In other words, these two right triangles are similar. So this is what happens when we scale a vector, and that's the idea of scalar multiplication. If we do have a scale factor k, which is a negative value, we are actually looking at the anti-parallel vector, which is in the same line as the first vector, but it's going in the opposite direction. In other words, we're changing both the signs of the delta x, which used to be positive in the blue case, and delta y was negative. We are now making the delta x negative and the delta y positive. So scalar multiplication can do a horizontal and a vertical reflection, but it's not actually changing the angle or the slope of the line that the vector lies in. The other type of operation that we have is vector addition. And in vector addition, we add two vectors together from tail to head. So it's like saying that we're going on a walk, and we might be starting at point A. And after point A, we go according to some change in x and change in y to a point B. Then that becomes our new point, our new starting point, and we move according to some other delta x and delta y instructions to get to point C. The sum of the blue vector and the red vector is really the result if you went directly from point A to point C without taking any other detour or path through point B. And so the vector in blue might be vector u, and the vector in red is vector v, and therefore the resultant, or the sum, or the net of the two vectors is the vector u plus v, which is the vector from point A to point C directly. And so if we combine these two operations of vector addition and scalar multiplication, we get something called the linear combination of vectors. And a unit vector, we know, is a vector that has a magnitude or length of 1. And we can refer to the unit circle, which is a circle of radius 1. We're using the same terminology of unit vector, which is a vector of magnitude 1. And then we have the standard or basis vectors, the I hats and the j hats, which allow us to see the basic directions of 0 degrees, meaning pointing to the right. This is an I hat vector, and 90 degrees, or pointing up. And so these are the two, if we make them look both about 1 unit long, these are the two unit vectors, and we can combine these in various ways to get any vector in the two-dimensional plane. So if we just take some summary of these two parent or basic or standard unit vectors, we have the polar form of the I hat vector is magnitude of 1 and direction 0 degrees. Then the delta x, delta y rectangular component form of this vector, if I sketch it, now keep in mind that the vector doesn't have to start at 0, 0, because translating the vector does not change the vector. We could start the vector at any initial and any final point. So if we go back here, we see that each of these little blue vectors is going one space to the right, so the delta x or the run is 1. And it's not going up or down, so the rise or the delta y is 0. Meanwhile, the j hat vector has no run, but a rise of 1. And so we can see that the magnitude comma direction for this vector is still a magnitude of 1 because it's 1 unit long, but the direction now is pointing in 90 degrees. And if we were to sketch this, we can sketch many, many vectors. Let me draw them in red. They can start anywhere we want, but they will always be one space long, pointing in the direction of 90 degrees. So if we have some other vector, say -3 to the left and 4 up, what we are really saying is that we have 1, 2, 3, 1, 2, 3, 4. We really have 1, 2, 3 negative I hats because they are anti-parallel to I hat. So we have negative 3 I hats, and then we are adding to that 4 positive j hats, because if we go from point A to point B to point C, the resultant blue vector is going to be negative 3 I hats plus 4 j hats as the sum, or what we call the linear combination of the individual I hats and j hats. So each I hat and j hat has been scaled, and then each of those pure horizontal and pure vertical components have been added together to give us a new resultant vector. The reason that this notation is so useful is because it avoids using brackets and commas, and it allows us to treat this mathematical object, this thing, with the same algebra rules that we've grown accustomed to with polynomials, for example, negative 3x plus 4y. We can still add like terms, and all of the rules that we're familiar with translate or transfer to this new notation for standard vector notation. So let's take a look at some examples. In exercise 5, we have a vector w from point A to point B, and so we want to draw this vector. So in the xy plane, we plot the point A, which is at 2, 3, and we are going from A to point B, which is at -1, -1. And then our vector, I'll illustrate it with a different color so we can see it better, is the red vector. Now, of course, that red vector doesn't have to begin at A. It can begin anywhere, because the vector will be the same as long as the horizontal and vertical, or the polar components, are identical to the original vector. Okay, so then what we want to do with this vector is to figure out the rectangular components from the rectangular coordinates of the points. Points have coordinates and vectors have components. So I'm going to call this vector w, and we have delta x. You don't have to put the subscripts a, b, but it is helpful so that we know the direction of travel from point A to point B. And just to remind ourselves, the definition of change is the final minus the initial. So this is what we're doing in the calculation. Of course, we do the same calculation when we work out slope, but then we make a rate of changes. So we make a fraction of the delta y over the delta x. So our delta x component is going to be -1 minus 2, which is -3, and our delta y component is going to be -1 minus 3, which is -4. That says nothing other than we go 3 to the left and 4 down. Or we could go 4 down and 3 to the left. The direction does not matter. In part C, we want to write this in, so this is part B. In part C, we are asked to write this vector w in standard vector notation, which says that we've got 3 I hats to the left, 1, 2, 3 of them, and then we have 1, 2, 3, 4 j hats down. And then we want to convert to polar components. So if we do that, we want to come up with the magnitude r, which I can call plane w without any vector bar notation. And we should recognize now the 3, 4, 5 triangle. The Pythagorean theorem is going to give us 5. We also have to come up with the reference angle, and keeping in mind that this vector AB or vector w, if we made the initial point the new origin, then the vector has an angle in quadrant 3. But first of all, the reference angle is going to be found using the inverse tangent of the absolute value of the rise over the run. In other words, the tangent inverse of the slope in absolute values, because we always have a reference angle which is a quadrant 1 sized angle, and then we adjust to place the reference angle into the appropriate quadrant. So here we have tan inverse of -4 over -3 in absolute values, which is just tan inverse of 4/3. And therefore our actual angle in standard position, a quadrant 3 angle, is going to be pi plus the reference angle. And lastly, we want to determine a vector v with the magnitude of the same magnitude as -4 I hat plus 4 j hat, that is in the direction of w. So we are looking here at vector w as having a certain direction, namely the angle that we found in part D. And we want the same magnitude as the given vector. So in part E, I think I can fit it here, we can see that the magnitude is going to be the square root of -4 squared plus 4 squared, which is going to be 2 times the square root of, 2 times 16 under the square root, which is going to be 4 square root 2. And so we want this new vector v to have a certain magnitude and a certain direction. And because we are using magnitude and direction, it makes sense to be efficient and write the vector v in polar form, because we are not told to use polar or rectangular components. In exercise 6, we are asked if we can perform vector addition and scalar multiplication for vectors given in rectangular and then in polar form. So for part A, let's consider two vectors. The first one, I'll call it vector A, and the x component is ax, and the y component is ay. And the second vector is vector B with similarly noted component form. And what we know about ax, ay, bx, and by is that this has to do with the change in x and the change in y. When we are adding two vectors together, let me make vector A a quadrant 4 vector. So we're going ax number of spaces to the right, and then we're going ay number of spaces down, according to how I have drawn vector A. And then let's make bx, for example, be negative and by be negative. So we are going to go to the left, and then we are going to go down for our vector b. And so the resultant vector goes from point A to point B to point C. It goes from the very beginning to the very end. And we can see that that resultant vector of vector A plus vector B is going to be the result of going ax spaces to the right and then minus the absolute value or the number of bx spaces going left. And so it really is that vector A plus vector B is going to be the sum of whatever ax and bx are, whether they are positive or negative. And similarly, we are going to get that the vertical component is going to be ay plus by. Because of the nature of delta x and delta y, we are adding and subtracting them according to their signs. Now, if we want to take vector A and scale it, what we're really doing is making a right triangle. Actually, let me make the right triangle first. And the right triangle has components or lengths of ax and ay, and the magnitude is a. If we scale that vector, I think I've got it twice here. We scale this vector, we're not just scaling the magnitude, but we're scaling the horizontal and the vertical components by the same scale factor. If that scale factor is k, in order to keep all of the angles the same and to preserve the similarity of the angles, we have similar triangles. And so we would have vector A being scaled by a factor k affects both the horizontal and the vertical components equally. And so in fact we can perform vector addition and scalar multiplication for vectors in rectangular form. But what about polar form? And in this case, I'm going to use two very specific vectors, vector I hat, which goes one space to the right, and so its polar form is given by a magnitude of 1 and a direction of 0 degrees. And I'm going to use vector j hat, which has, I'll draw it properly, it goes up one space, and so it has a magnitude of 1 also and a direction of 90 degrees. Well, if we take the j hat vector and we want to scale it, let's say scale it by a factor of 3, so we end up with this new scaled or 3 times as long vector. The question is, do we triple both the magnitude and the direction? So if we want 3 times vector I at 90 or 1 at 90 degrees, does this give us a magnitude of 3 and an angle of 270 degrees? Well, it turns out that we are only changing the magnitude and we are not changing the direction, so we do not change both components in polar form by scalar multiplication. And what if we take the two vectors and add them together? Can we add the two vectors I hat plus j hat in polar component form? Do we simply add the two magnitudes and add the two directions? Well, if we look at a picture of the two vectors, I hat and j hat, we have them here. And let's copy and paste them. I'll redraw the vector I hat. If we want to add them together, we need to go from point A to point B, and then from point B to point C, which means I need the vectors in head-to-tail format. Now, I don't have to start with the blue vector. I can start with the red vector. And so if I go from point A to point B and point B to point C, my resultant vector is going to be the hypotenuse going from A to C directly. Because of Pythagorean theorem, we have a right triangle. We know that we have a base and a height of 1, and so by Pythagorean theorem, the magnitude, or the hypotenuse, of this vector is going to be the square root of 2, which is not the magnitude we get by simply adding the two magnitudes in polar form. Furthermore, this vector AC is not in the direction of 90 degrees, and so we do not add the directions together in polar form. So it turns out that while for vector addition and scalar multiplication we do have to have rectangular form, we cannot use polar form for performing these operations. Therefore, we really need to be working with the rectangular form to be combining our vectors.